and welcome to our next module on space-time codes. Let's start with a brief outline of today's talk. We would look at real orthogonal design. We'll look at generalized real orthogonal design. We'll revisit that. And then we have studied complex orthogonal design. What we will do is then move on to quasi-orthogonal design, which will help us move from single symbol decoding to decoding in pairs. And finally, we would look at some examples. So let's see how we can proceed. We have done some of these earlier and they're important enough to be revisiting them again. So let's go with that. So let's recollect what we learnt about real orthogonal design in the context of space-time block codes. We defined a real orthogonal design of size n as an n cross n matrix. So it's a square matrix G with the entries coming from x1, x2 up to xn, such that G transpose G is summation I equal to 1 through n xi squared in, where in is an identity matrix. And we have also seen that real orthogonal designs exist for limited number of cases, namely for n is equal to 2, 4 and 8. And we also note that G is proportional to an orthogonal matrix. We looked at some examples. Well, there are 3 examples possible: G2 for n is equal to 2, G4 for n is equal to 4. So both of these cases, if you do G2 transpose into G2, you will get elements only along the diagonal, and off diagonal will be 0. And finally, the example for n is equal to 8, which will allow you to transmit 8 symbols through 8 antenna elements in 8 time slots. So please note the columns correspond to the antenna elements. So clearly this is the symbol that I will be transmitting from antenna element in time slot 1. The first row corresponds to what we are going to do in time slot 1. So if I were to implement this in real life, time slot 1 I will send out x1 from antenna element 1, x2 from antenna element 2, so on and so forth till x8 till antenna element 8. Having done that, we go to our next time slot where we load minus x2 from antenna element 1, x1 from antenna element 2, x4 from antenna element 3, so on and so forth till x7 from antenna element 8, and again I fire them. And then I go to the next time slot, which will transmit row 3, and we repeat this till we are at the last row, which is the time slot 8, where we send out these 8 signals. So what we realize is at the end of 8 time slots, we have been able to transmit x1 through x8. Therefore, the rate is 1. And we have seen that this orthogonality leads us to single symbol decoding. Then we said that we need to go beyond n is equal to 8, and therefore we learned to tweak the real orthogonal design, and we went on to study generalized real orthogonal design, where the matrix, generator matrix, is T cross n, where we go from plus minus x1 plus minus x2 up to plus minus xk. Again the constraint is gt. G is nothing but summation I equal to 1 through k xi squared into this identity matrix. But please note that this time we use this T time slots, and therefore since we have been able to send k symbols, effectively the rate is k over T. So we compromise on the rate. Then we would be interested in finding out the smallest value of T. So we would like to send out the symbols in minimum number of time slots, because T determines the decoding delay, because it is very obvious that we cannot start the decoding process unless and until all the symbols of all the T time slots are received. So we define the delay optimal as an orthogonal design with minimum possible value of the block length T. We did this definition earlier. Here is an example. This is an 8 cross 7 generator matrix clearly it will be using 7 antenna elements. It's so this x1, x2 up to x7 goes through the first time slot and then the next and next one, but we are using 8 slots to send out 7. Then we moved on to complex orthogonal design when we remove this condition of real symbols. So our constellation could be QPS, K, QAM, but here we would like to use complex design, and again we can verify that this is the only possible solution where G Hermitian G gives this x1 squared plus x2 squared into I2. This is the Alamuthi code we have studied, and this is the only possible design, forcing us to look at generalized complex orthogonal designs. Here we start with the possible symbols coming from 0 plus minus x1 plus minus x1 star, which is the complex conjugate, plus minus x2 plus minus x2 star, and so on and so forth up to xk star. And we again put this condition G Hermitian G is equal to some kappa times this standard I is equal to 1 through k summation xi absolute value squared into this identity matrix cross n cross n. Then we made some observations that the generalized complex orthogonal design provides a diversity of n cross m. So this is one of the very important things. We get tremendous amount of diversity gain using space-time block codes, and n is the number of transmit antennas and m is the number of receive antennas. So it's directly the product. The other good part is the decoding complexity. The maximum likelihood decoding does symbol by symbol because we have been able to decouple the decoding operations at the receiver by using the information about the channel gains. So what we see is that we have 3 independent parameters, n, k and t. N is the number of transmit antennas I can fix at will. I can have the number of time slots k, the number of time periods t, and the number of symbols k, and I can play with them and come up with a generative matrix which can be denoted by G sub nkt. Now we move forward and we see that we have already available some real orthogonal designs. Can we construct generalized complex orthogonal designs from this real orthogonal design? If we have that, then we have a recipe. So answer is yes, it is possible to construct a complex orthogonal design using real orthogonal design. When we say real orthogonal design, we just mean that we have the generator matrix for that. So consider a rate R real orthogonal design with transmission matrix G of size t cross n. So this could be a generalized real orthogonal design. So we denote the conjugate of G by G star, and this is nothing but replacing all the elements xk with xk star, x1 by x1 star, and so on and so forth, and therefore we construct a complex orthogonal design as follows. Gc, right, is nothing but G, the generator matrix of the real orthogonal design, and G star. We can easily verify that if you take this and compute Gc Hermitian Gc, then you can check with the properties of G, which is itself a generalized real orthogonal design, to give you the following. So thus by construction we have generalized complex orthogonal design, and we can go on and on with this. Let's take a very quick example. So we would like to consider a 3 antenna system. There are 3 transmit antennas, so n is equal to 3, and we would like to construct a generalized complex orthogonal design using a real orthogonal design. So what we need to do is we will put the first G here and G star here. So if we substitute this G by its elements here, I have this design that we studied earlier. Again, this is a 3 antenna system and we have 4 time slots, so it is kind of a generalized real orthogonal design. But please note, in 4 time slots it is able to send x1, x2, x3 and x4. So it is a full rate generalized real orthogonal design. All we have to do is substitute each xi by xi star and we fill up the lower half of this matrix. So we have just mechanically substituted the complex conjugate of each of this. So the top portion is my G and the lower portion is my G star, and lo and behold we have our new constructed complex orthogonal design, generalized complex orthogonal design available, and one can verify that this will indeed give me G Hermitian, G will give me elements only along the diagonal. Now please note here n is equal to 3. So if you see the subscript n is equal to 3, 3 comes in here, and we have used 4 symbols to be transmitted, as you can see x1, x2, x3, x4. So k is 4, so the next number is 4, and if you see this total design will require 8 slots. Right? The number of rows represent the number of slots, time slots, so 8 is the third number here. So we can denote this generator matrix as G348. Later on we will look at the performance of this as we go along the lecture. So if you do the computation of this matrix G Hermitian G, you will get the following. Along the diagonal you have summation I is equal to 1 through 4 xi squared, and rest of the terms are all 0. So this is a generalized complex orthogonal design. So k is 4, t is 8, so consequently we have rate 1 by 2. Please note here the top half was a full rate, this guy is also full rate, but we have not increased the number of symbols, they remain from x1, x2, x3 and x4. Consequently, doubling the number of time slots had led to halving of the rate. So we pay in terms of rate. So we were able to easily design it, but the rate has gone down. Let's consider another example. This time we have n is equal to 4 transmit antennas. So clearly there are 4 columns, and then this is a 4-3-4 design. So we are trying to basically try to see that 4 transmit antennas, n is equal to 4, but the number of symbols that we are sending is only 3. So x1, x2 and x3 and their complex conjugate. So the second number is 3 and the number of time slots is 4, that gives you the last 4. So this is a G434 design. K is equal to 3, t is equal to 4. Now the definition of rate is k by t, so 3 by 4. It is also clear from this that I have taken 4 time slots to send out 3 symbols, so the rate is actually 3 by 4. But what is very interesting is that even though I have 4 antennas and the rate is not too bad, in the first time slot 3 antenna elements are firing and the 4th one is silent, there is a 0, I do not transmit anything. In the next time slot antenna 1, antenna 2 and antenna 4 are firing, but antenna number 3 is silent. Similarly, antenna number 2 does not emit anything, and in the last time slot the first antenna element does not radiate anything. So in every time slot one of the antenna elements is silent, right? This is very interesting. This has an implication on the average power that we are transmitting through the antennas. The rate is not bad, right? And this is a complex orthogonal design, of course generalized complex orthogonal design. So these are very interesting variations that give you some additional benefits without compromising much on the rate. So, this thing shows you that each and every time slot makes sure that one antenna element is silent. So, it has a very interesting implication on the power consumption. That is also an important parameter here. Now, let us talk about shortening, where we had earlier observed that it is possible to obtain code designs with fewer number of antenna elements simply by dropping columns. Why? Columns represent the what you transmit from a certain antenna number 3. So, this column represents what you send from antenna element 1, this column represents what you send from antenna element 2 along the 4 time slots, from antenna element 3 across the 4 time slots. So, what we do is we look at the earlier example here, and we are curious to see what happens to this code when you simply drop the last column. Okay? We would like to say that we are now, instead of using 4 transmit antennas, we would only use 3 transmit antennas. So, we just keep the last antenna element turned off across all the time slots. So, if you do so, you will get this following code matrix. Now, again, what have we gained? We are again transmitting x1, x2 and x3 using 4 time slots. So, the rate has not changed, but magically now we were designed for 3 transmit antennas. Is it orthogonal? Sure. Now, we dropped the 4th column, but we could have as well dropped the 2nd or the 1st, any one of them, because no antenna is holier than the other antenna. So, we could have obtained deleting other columns, another parallel G334 design, and then if we are not satisfied and we want to go to a 2 antenna system, I would again like to drop off any one of further to get a G234 design. That will be a design for n is equal to 2. So, this shortening method is again giving me a mechanism to use fewer number of antenna elements, right, but still giving me this design. So, if I draw this 3rd column again, so I am left with this matrix which corresponds to only 2, n is equal to 2 antenna elements. But what is very interesting is we have x1, x2 and x3 all 3 being sent over the 4 time slots. So, we have not really compromised on the rate. Rate still remains 3 by 4, but the number of antenna element has gone down. So, it will have implications on the diversity gain. So, yes, there is no free lunch, we are cutting back on the number of antenna elements and leading to the lowering of the diversity gain. But shortening is a very simple way to make my life simple. From a larger design, I can go down to a design with fewer number of antenna elements. So, here I have dropped the 3rd column as well. So, effectively from the original design of 434, I have been able to drop the last 2 columns and retaining the first 2 columns, and I still have this design. But each time we do so, we are paying in terms of the diversity, because diversity is n into m, where n is the number of transmit antennas which we have halved, and so the diversity gain will also drop down by half. We have observed this, that the diversity gain is n cross m. Please note that the transmission matrix of G434 is not unique. So, again we have here another parallel design, an alternate design with rate 3 by 4, it is given here. Let us talk about this as G prime 434 to distinguish it from the original design that we looked at, G434. So, this is different. If you do not remember the earlier one, we bring it in. So, this is the first design we saw, and this is the second design. Here if you see, it is a more simpler way. So, we have x1, x2, x3 from the first three elements, nothing from the fourth element, whereas in this first design we had the complex negative earlier and so on and so forth. But again, zeros, 1 0 in every row, 1 0 in every row. Now you can check that both of these designs are orthogonal. Now it can be shown that the rate of a generalized complex orthogonal design cannot exceed 3/4 for more than 2 antennas. So this has been shown earlier. So this is the best we can do for a generalized complex orthogonal design for more than 2 antennas. Now let's move a little bit ahead and talk about something called as diagonally orthogonal space-time block code. So we are now looking at different variations and what we can buy, what we can compromise and sacrifice. So diagonally orthogonal space-time block code is a T cross N transmission matrix G. Again, clearly it is using complex elements from x1, x2, x3 and so on and so forth up to xk, all real and complex, and the condition is that G Hermitian G should be a diagonal matrix. Earlier it was something multiplied with an identity matrix, but this time I am happy if it is just purely a diagonal matrix. So D is an n cross n diagonal matrix, and what will be the diagonal elements? Well, diagonal elements can be of the type some coefficient absolute value of x1 squared plus some coefficient absolute value of x2 squared and so on and so forth up to some coefficient absolute value of xk squared. So these are the diagonal elements of this diagonal matrix. Let's look at a quick example of a transmission matrix for a diagonally orthogonal space-time block code. So here what we have is, if we count the columns 1, 2, 3, 4, 5, we have n is equal to 5. So we are going to use 5 antenna elements to transmit, and if you count the number of rows 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 time slots with which we are going to send this out. So T is equal to 11, n is equal to 5, and if you observe carefully we have x1 through x7 only. So we have k is equal to 7. So 7 symbols being transmitted using your 11 time slots. So rate is obviously 7/11. We can carry out for our sanity check G Hermitian G, and what we get is as follows. So up to this point it looks pretty much like your regular generalized complex orthogonal design, but here if you see the last diagonal element, we have some coefficient xi squared, I is equal to 1 through 3, and then from 4 to 7 this one. So therefore we could not represent it as something multiplied by an identity matrix. So thus we have this design. This is clearly, had a similar expression come in the last diagonal, then we would have said that no, it is really a generalized complex orthogonal design. Now what we have studied so far is this single symbol decoding. This has really improved our decoding complexity, and we don't have to worry too much about doing exhaustive search over a pair. So the two main properties of this orthogonal design are full diversity. Okay, we have looked at so many examples that is giving us full diversity, and simple separate decoding. These are the two trump cards that we have. But we have seen also that full rate complex orthogonal designs do not exist for n is equal to 2. We made that observation. So we have to relax something to gain something more. can we relax the simple separate decoding constraint and gain in terms of the rate of the code? Which is more important? Separate decoding constraint, which has a direct implication on decoding complexity, or the rate of the code, which has a direct relationship to bandwidth. So, on one side we have to weigh whether we would like to gain in terms of bandwidth or we would like to reduce the receiver complexity. These are the two requirements, and orthogonal codes so far were giving us the single symbol decoding, thereby reducing to the extent possible the receiver complexity, and at the same time giving us full rate. Or wherever rate was not possible, for n is equal to 2, we do not have full rate codes. So, question is now, can we maybe go for double symbol decoding or pairwise? So, let us explore that possibility. This is done in a new class of codes called quasi-orthogonal space-time block codes, or QoSTBC for short, quasi-orthogonal. So, we are going to relax some properties of the orthogonal design. In quasi-orthogonal space-time block codes, pairs of symbols can be decoded independently. So, we have compromised in terms of single symbol. We are now gone back to pairs. It is not too bad if the number of symbols are not too large, right. So, we are now going to look at pairs of symbol as opposed to single symbol decoding. Let us start with an example. Consider the following quasi-orthogonal space-time block code. So, here if you see, there are 4 antenna elements, so n is equal to 4, and here if you see, we are using 4 time slots. So, we are back in business. Earlier, to transmit 4 symbols, we had started to take more number of time slots, thereby reducing the rate. But here again we are back in business, we are transmitting 4 symbols over 4 time slots, and thereby we are looking at the full rate codes. But then what happens to the orthogonality? Clearly this is not an orthogonal design. So, let us check it out. We do this multiplication G Hermitian G. What does it give us? Well, if you do that, you get as a first diagonal element x1 absolute value squared plus x2 absolute value squared. Same for the second, and then this one is x2 absolute value squared plus x4 absolute value squared, and similarly here. So, what has happened is we have kind of coupled these. But what have we gained? Well, the QoSTBC is a full rate because it sends 4 symbols in 4 time periods. So, even though it has 4 antenna elements, the diversity is only 2. That is the question we have to ask ourselves. Is diversity 2? Why? Why are we saying that the diversity is 2? Can we observe this and say the diversity is 2? That is, whenever we are decoding at one time only 2 symbols, if only one of them fades, the other one can be used, so the diversity gain of 2 is there. Similarly, a diversity gain of 2 is there. Had there been 4 elements added together, then we would have looked at a diversity gain of 4 as required, because n is equal to 4, but the gain is 2. Please note, intuitively we have explained that diversity gain comes from the fact that each of the symbols coming from different antenna elements goes through a different path and a path gain. Now, if that is fading, then if we assume independent fading, if one of the symbols is fading, the other one is not. So, the diversity gain comes from that. Here, if you look at this carefully, you can see immediately that the diversity gain is 2 and not more. So what does it mean? Well, the first two antenna elements always transmit X1 and X2, while the remaining two are always transmitting X3 and X4 and some combination thereof, but that's it. So effectively what we have done is we have just concatenated two Alamuthi codes, and we are trying to say that we are sending X1 and X2 and X3 and X4, but we are just using Alamuthi code 2 times in a row. But Alamuthi will only give me a diversity gain of 2. Rate is preserved because 2 times in a row we are using a full rate code, so the effective rate is 1, but diversity there is no improvement. So to achieve full diversity, instead of substituting Xk by Sk in the transmission matrix, we can use the following substitution to construct the code word matrix. So now we started mixing. Earlier, instead of X1 being dependent only on S1, I have made X1 dependent on S1, S2. Now the first transmit antenna will be dealing with S1 and S2. The second one is now dealing with S2 and S3 and S4. So I have brought in back this other two symbols. I have started mixing them up and thereby hoping to get diversity. Okay. So what does it lead us to? Now if you look at this C Hermitian C, you will get this kind of a solution, right? And what is A? A is given by this. So you again immediately get back all the 4 terms in summation. Immediately your diversity jumps to 4, because see, we assume all the signals are fading independently. So if you are taking the sum of all the 4 symbols effectively, even if one fades, the other 3 will not fade, giving you that diversity gain. They are independently fading. So if you carefully observe, this C Hermitian C is immediately leading you to a diversity of 4. So now let's consider another quasi orthogonal space time block code. These are best understood using examples. Now if you logically partition it as follows, okay, so we divide it into 4 quadrants and we say that the first quadrant is GA X1 X2, because please note it only depends on X1 and X2. This one depends on X3 and X4, this is depends on X3 and X4, this one depends on X1 and X2. So I do that X1 and X2, X1 and X2, but if you look at carefully, these two are complex conjugates. So this is G1 X1 comma X2 and this is G1's complex conjugate. Similarly, this is G3 and this is negative sign complex conjugate. So I get X3 X4 GA and minus GA complex conjugate. So we write G as follows, we just now observed. But what is GA? Well, this is the standard Alamuthi code, right? So we denote the ith column of G by chi I, and we look at chi 1 chi 2 inner product, that is 0, chi 1 chi 3 0, chi 2 chi 4 is 0, chi 3 chi 4 is 0. So we are looking at this pairwise orthogonality and therefore the name quasi orthogonal. So here this notation is the inner product of the vectors. So one way to look at it is that the subspace created by chi 1 and chi 4 is orthogonal to the subspace created by chi 2 and chi 3. So therefore we have this quasi orthogonal codes, right? This justifies the name. Let's look at yet another example of a 4 cross 3 quasi orthogonal space time block code. Okay, 4 antenna elements as shown by the 4 columns. Well, we don't want them to disappear, all of them, and we have got 4 time slots, and there is your quasi-orthogonal space-time block code that we have seen. Alright. So, if you make this observation, this is only a function of x1 and x2. This guy, this quadrant is GA star, which is the complex conjugate. This is GA x3 comma x4, A star stands for the Alamuthi, and this is minus GA x3 comma x4. So, this is what we have done this, and now let us drop one. So, we erase one of the columns. So, suddenly we are left with 3 antenna elements, but please note here the beauty, we still have x1, x2, x3 and x4, all 4 symbols being transmitted in 4 time slots. So, just by dropping this column, we reduced our diversity gain, but of course, fewer number of transmit antennas has other practical benefits, and so we replace that 4 columns to 3 columns. Okay. So, we go this one and we write it properly and we express it in terms of the 3 columns. So, we have now obtained a simple design for 3 transmit antennas. So, this using this quasi orthogonal space-time block code, we are now going to send 4 symbols x1, x2, x3, x4, which will represent, if I map S1, S2, S3 and S4 in 4 time periods. So, clearly the rate is unity. Now, just let us spend a couple of minutes on our design targets. What are the design targets, what we gain, what we can compromise, is there a free lunch? Let us look at that. So, the design targets for space-time block codes are as follows. First is the rate of transmission. Direct implication on the bandwidth. Today all practical designs require us to transmit data at higher and higher rates. So, one of the greatest benefits is the rate improvement. We can get full rate codes, and therefore we would be very happy to have rates as high as possible as one of the design criteria. The number 2 important thing is the diversity gain. Okay. We have been talking about it all along. Space-time block codes give you humongous diversity gain, especially at high SNR conditions, and this comes from our rank criteria that we discussed earlier. Then we have also got multiplexing gain, because simply because of this MIMO system you have different channels, and different channels independently give you multiplexing gain. Then we had looked earlier into the determinant criterion, where coding gain was also coming from the design of good space-time block codes. So, that is an add-on. And finally, there is a diversity multiplexing gain trade-off, okay, that comes from the non-vanishing determinant condition. We have not talked about it in detail, but intuitively you can look at either from the independent channels that we get from different antenna elements, we have diversity, or we can utilize it as a multiplexing gain, but not both. So, we have a trade-off of sorts. And finally, we have been talking about the single symbol decoding and at most a pair-wise decoding. So, decoding complexity is important, especially if you are looking at larger and larger constellation size. So, you have this platter of constraints or requirements or design targets, if you will, that we have to keep in mind while designing or choosing good space-time block codes. Let us now move over to the performance of some good space-time block codes. So, if you see, on the x axis we have the SNR in dB, on the y axis we have the bit error rate. Okay. Now, we have lots of curves here. Let us look at this top one, which is the worst performing curve. It is for a single antenna system. So, you do not have space-time block codes. For the sake of discussion only, let us make sure that we understand that m is equal to 1, that is, it is a single receive antenna. So, when we talk about multiple antennas, we are putting them at the transmitter. So the first case is SISO, single input single output system, no diversity gain whatsoever, and we have a happy go lucky curve going up here. Okay. Not too good, not too bad, but can we improve it? So we immediately put in two antenna elements and we have the second curve, a quick dip here, and the slope increases, and the slope is an indicator of the diversity gain. So just by observing these two curves, we can say that look, putting two antenna elements at the transmitter has immediately given me a diversity gain of 2. The other important thing is to note that the slope increase means that these paths diverge, these two curves diverge as we go along, which means that at higher and higher SNRs the diversity gain is more and more. So the diversity gain, the real benefit comes at higher SNRs. Then why should we stop? We go ahead and look at 3 antenna systems, but this is a case, we have looked at many n is equal to 3 cases, but this is the rate half and modulation scheme is QPSK, and then we have this curve which is giving you the 4 antenna systems, and then again we have some overlapping curves with 3 antenna and 4 antenna systems. So the symbols are plotted on top of each other, showing that they are coincidental with rate, full rate and BPSK. So the point is that as we go from 1 antenna element at the transmitter to 2 antenna to 3 to 4, this clearly diversity gain, slope improves, improves and improves, but the improvement is decreasing. So we have a humongous improvement from n is equal to 1 to n is equal to 2. Yes, improvement from n is equal to 2 to 3, but not so much as we saw in the first case. And we go from 3 to 4, improvement is there but even less. So we see some sort of a law of diminishing return as we go along. So we just cannot say that look, give me as many antennas and I'll pack them in my transmitter. After a while it really is not worth it. So this slide basically summarizes the plot that we have seen just now. We have assumed a quasi-static Rayleigh fading channel. So over the symbol that we are transmitting, the channel really doesn't change. Of course, we are using MLD coding at the receiver, and we have looked at the plots and compared for n is equal to 1, 2, 3 and 4, provided there are only one receive antenna at the receiving end. And this table summarizes which space-time block code actually did we use, what modulation scheme did we use. So if you see, then there were 6 curves, there were 4 distinct curves, there were some overlapping curves, and so there are 6 rows here. So this first case was the standard BPSK, which is a real constellation. Obviously we can't use space-time block codes, so rate is not applicable here. In the second case, when 2 antenna elements were used, we used QPSK. So we had 4 symbols to choose from, which is obviously a complex constellation, and we used complex orthogonal design. The only known Alamuthi scheme we used, full rate. The third one, when we moved on to 3 antenna elements, we used a real orthogonal design. Using this generalized real orthogonal design we studied, full rate. And then again for n is equal to 3, we just don't have to go with a real design, I can go with a complex design. And complex design QPSK and this G348 we have already studied in today's lecture, and it is rate is 1 by 2, right. And then if you look at 4 antenna elements, again we have an option for real design or a complex design. So what it illustrates is that you have a choice. You can go with a real design, we have looked at so many examples, or a complex design, generalized complex orthogonal designs. You can have a choice for modulation schemes as well. And so far we have stuck with simple QPSK, BPSK types. It doesn't stop you from going to slightly higher modulation schemes. Well, you have to see what do you sacrifice in terms of the rate. So, just to bring that to a conclusion, for the n is equal to 4 QPSK condition. So, if you look at this last row, right, if we have to just take this last row into consideration, what exactly did we do? Well, we have a complex, generalized complex orthogonal design given by this thing G448, 4 antenna elements using 8 time slots, sending only 4 symbols. So, we have a rate of 1/2. This is the case we just now studied. Okay. So, this is the last curve that is coming out from the design we just now talked about, m is equal to 1. Now, a couple of observations, we have made some of them earlier. It is interesting to know that the performance for rate r is equal to 1 BPSK is identical to rate half QPSK for n is equal to 3 and 4. That is why they were overlapping. This is interesting to note. Also, that the law of diminishing return was observed, right, and as we go to high and higher SNR, then the diversity gain increases. This improvement we have seen earlier also. So, we can look at some numbers which are given here, which tells you that exactly you get a better diversity gain at higher SNRs. Just try to conclude this talk by looking at now what happens if we put in 2 receive antennas. So, n is equal to 2. So, my variable now is n, where I vary my n from 1, 2, 3, 4. So, up to 4 transmit antennas and 2 receive antennas. Clearly, we have seen that the diversity gain is m into n. So, if you compare the first case of single antenna at the transmitter, but 2 antennas at the receiver. So, you get some gain, but again if you look at 2 antennas at the transmitter and 2 antennas at the receiver, you get the following curve, and again at 3 antennas at the transmitter and 4 antennas at the transmitter, you again get this law of diminishing return. Once again for 4 antenna and 3 antenna curves, this either you use rate 1 BPSK or rate half QPSK, you have the curves coinciding. So, this cements the fact that we have a big potential for performance gain if we use space-time block codes, and no wonder for newer wireless communication standards they are becoming more and more popular, and we are going to use space-time block codes to improve the performance of wireless communication systems. Let us look at our lecture, what we have studied today. So, we revisited real and complex orthogonal space-time block codes. We talked about generalized real orthogonal designs and generalized complex orthogonal design. Then we talked about diagonally orthogonal space-time block codes, followed by relaxing the condition of single symbol decoding, and we went on to quasi orthogonal space-time block codes. We then talked about what are the design criteria, what are the design targets, and finally we looked at the performance curves for n equal to 1, 2, 3 and 4 for different number of receive antennas. With that, we conclude our lecture today.